Hey guys, Mr. B here, and in this video we're going to be going over the chapter 1.4 notes on presenting scientific data. Alright, so in this section we're going to be looking at how scientists organize their data and how they communicate their results, and we'll also be taking a look at some data tables and some graphs. Alright, so how do scientists organize data? So a lot of times, of course, when we're doing science and doing experiments and making lots of observations, there's lots of things that we need to write down and information we need to make note of so we can use it later on to come up with some conclusions. We can organize our data a lot of times either using data tables or graphs. Okay, data tables are usually helpful to organize the information that we are getting while we're doing an experiment, and graphs are usually made after the experiment's done with the data we've already got to then help communicate results to people. Okay, so data tables are more commonly used during the experimenting process. Graphs are used afterwards. So as to what a data table is, sometimes students for some reason get data tables and graphs mixed up, but a data table is usually a way that we can organize our information in columns and rows. Okay, and a lot of times on our data table we'll have our manipulated variable and our responding variable, so we can see how the thing that we're changing is affecting the thing that we're trying to measure. So here would be an example of a data table. Okay, and this is the average annual precipitation for selected U.S. cities. So basically it's like average rainfall for cities around the U.S. Manipulated variable would be the location. So we can see that we are changing the location. Buffalo, New York, Chicago, Illinois, Colorado Springs, Colorado, Houston, Texas, blah, blah, blah. And so we change the location, and then what we're measuring, what we're hoping is then going to change based on what we're changing is how much rainfall. Okay, so we have our manipulated variable in this column, which is the different cities. And we have our responding variable, what we're measuring, in the other column, and that's how much rainfall that city is getting. Now, obviously, many data tables are more than just simply two columns with rows. Sometimes there's 3 or 4 or 5 columns, and they can be quite large. But I'd recommend that if you have a lot of data, it's probably best to put your data in multiple data tables than make one data table that's really big. Okay, just my personal opinion. All right, as always, we are not going to be answering the practice problems in this video. If you want to see me go over those, there's a separate video for that, so you can watch that one. But this one, we're just going to be talking about the information. Okay, so as for graphs, a lot of times when we take that data that we are gathering, we can put them into different types of graphs. If of course, the data we're getting is numerical, okay, with numbers. Sometimes you make a data table and you write down observations, which are not numerical. It's just simply like things you see before and after and during. So, but if we do have numbers, we can put those things into a graph. Line graphs are very, very common and probably the most useful for showing changes in a variable over time. So if we want to see a relationship between two things, a line graph can really help us do that. A lot of times we will put the manipulated variable on the horizontal or the x-axis, and we'll put the responding variable on the vertical or the y-axis. Okay. Now line graphs are primarily helpful when we look at the slope of them. Now, if you don't know what slope is, this is hopefully something you've learned by now in 9th grade. You should have learned this in math class, I'm sure, in your 6th or 7th grade years. But the slope of any line graph is the vertical change divided by the horizontal change. Okay, a common equation that we use is rise divided by run. Otherwise, another way that you may have heard of it is could be like y2 minus y1. Oh, let me change this. There you go. Could be like y2 minus y1. There you go. Sorry. Y2 minus y1, and then that could be like divided by x2 minus x1. Right? Something like that. Like that. That's one maybe you've seen before. Or if you haven't seen it like that, maybe you've seen it as like, change in y divided by change in x or something like that too. They're both the same thing. Okay. Either way, if you've never used the slope equation or found slope before, or you're not good at it, we're going to be doing more with that in this class, okay? So it's not super hard to do, and it's really, really good information that can give us a lot of insight into what's going on in an experiment. So, all right, so just to recap here, the rise represents the change in the vertical or the y variable. The run represents the change in the x variable along your graph. And these changes can be in a direct proportion, which means that the ratio between the two variables is constant, or the fraction. Or basically what a direct proportion is saying is if you increase one of these values, the other one will also increase by the same amount. Or if you decrease one of them, the other one will decrease by a set amount. So a direct proportion just means that they are related in the fact that if you change one variable up, the other one will go up. If you change one variable down, the other one will go down. Okay, that's what a direct proportion is. So a typical line graph that has a direct proportion would just be a linear line, okay, that just goes like straight up or goes straight down or even lays flat, but either way it's straight, there's no curve to it, okay? That is what we call a direct proportion. So I'm sure many of you guys have seen these types of graphs in math all the time. They're very, very common. So this graph is distance versus time, I believe. That's what it should say is time. Okay, so this is distance versus time, which is, we'll be looking at distance versus time graphs later on in this class. So, okay. However, not all line graphs are, wow, what's going on with my graphs here? I don't know. Anyway, not all line graphs are direct proportions. Some are inverse proportions. So what does that mean? What is an inverse proportion? An inverse proportion is where one variable goes up and the other one goes down. Okay, so typically the graph isn't going to be a straight line. It will be usually going downwards, this way, right, downwards. So let's say miles per hour versus hours. So the faster you go, or the higher your speed is, right, the more miles per hour you drive, the less time it will take you to get somewhere, right? So as miles per hour increases, the amount of time it takes decreases. So you're going to see a graph that's going to kind of curve downwards like this, or have a downward curve. So again, I don't know why this image is not showing up, but you know, imagine just a line or a curved line that's going down like that. That would be an inverse proportion. So, okay, bar graphs. So let's talk about bar graphs here. People love bar graphs. Wow, I don't know what's going on with my graphs and why they're not here. Anyway, bar graphs are oftentimes used to compare numbers to each other. Okay, so I know that like students really like bar graphs because they're really simple to make and they're easy to read. But bar graphs are not helpful unless you're trying to compare like multiple things to each other, okay? If you're taking data and you want to look at how this data affects that data, you want a line graph. If you're taking data and you want to see how this information compares to that information, then you want a bar graph. So bar graphs are good to compare things, measurements, amounts, or changes, and it's easy to see how data from one set compares to data with another set, okay? But bar graphs don't help when you're trying to find a relationship between how this thing affects that thing. So this picture, which is not showing up here, and I apologize again, I don't know why my thing is having problems, but it would have a bunch of different bar graphs of annual precipitation in different cities. So it could be like, you know, one bar graph is New York, another one's like, you know, Seattle. And so some bar graphs are going to be taller than others, which shows you that these cities have more rain because the bar graphs are taller. And these other cities, which are maybe down here, have less rain because they're shorter, right? So it's a really quick way to just compare different places or different things with each other visually. And you can just see, oh yeah, that city has the most rainfall, that one has the least. So as for circle graphs, we're not really going to make any circle graphs in our stuff for this quarter, or bar graphs really. But circle graphs are basically used to show parts of something compared to a whole, or percentages a lot of the times. So you usually have a circle, and the circle is divided into different parts, and it shows the size of those parts compared to the whole thing. So this graph here would be like the composition of Earth's crust. So out of all of the elements in Earth's crust, this is the breakdown, right? Like this percentage of it is oxygen, this percentage of it is silicon, this percentage of it is aluminum, and blah, blah, blah. So it shows all the different parts compared to the whole thing. The problem with circle graphs is that they're a lot more challenging to make by hand. You kind of want to make them in a program on a computer. But again, they're really only good when you're trying to like see how something affects a whole. So they're good for surveys, right? If you're to take a survey of, what lunches do students like the most, and it's 10 different lunches, and you poll the whole student body, and of this 100%, 50% of students like this lunch, and 35% of students like this lunch, and blah, blah, blah. So it's good for surveys and stuff, but again, not so much in what we're going to be dealing with. So all right, last part here is about communicating data. So once we've got all of our data, we've maybe even made it into graphs and stuff, how do we communicate that information out to other people? So again, the point of science is to learn information, gain knowledge, but also to then share that knowledge with the whole, collective human race and not just keep it to ourselves. So a lot of times we'll communicate our results by either writing in scientific journals or speaking at conferences. Now, scientific journals, nowadays are typically going to be digital, okay, online on the internet. There's a lot of different high prestigious websites and places that will publish your work that people can buy those digital papers and read them. Of course, back in the day, they were physically printed, but nowadays you just find them online. Or speaking at conferences, which is still very common. So there's conferences that are held at universities and colleges, or at companies, and researchers or whatever will come in and talk to a large group of people about their work that they've done. Or there'll be entire conventions, right, that are set up over a weekend for thousands of scientists to come together to talk about different topics that pertain to the field that they're in, so they can learn about what's up and coming, or, new cutting edge technology or whatever that's in their field. So very, very common thing that still occurs today. But understand that, of course, all of this data, and even when you're presenting information to other scientists, they might interpret the data that you have differently than the way you interpreted it. So typically, before you go and publish anything or put information out there, it's really important to let other people look at it, to review it, to encourage comments or suggestions or questions or criticism about your work before you go and put it out there. And the main reason for that in these peer reviews is to make sure that what you're putting out there is accurate and it's honest and it's not biased. Okay? Otherwise, what can happen, and I'm sure many of you guys have maybe seen this in the media in the past, is scientists may publish information that isn't exactly accurate or true, and then later on they get flacked for it because people go, oh, a new study, published by scientists and blah, 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 has found to be, incorrect or fake. And, all of a sudden now this scientist who maybe worked really hard on their stuff, they get fired, or their image gets tarnished because people now don't take them seriously anymore because they published this work that was just completely wrong. Or what the worst thing is people might actually believe that work. They might read that paper or read that article and believe that it's true and real. And now you've influenced people in the world to then think that something works the way that it shouldn't be, right? And a prime example of this, and so right now, basically, I'm recording this video during COVID. So COVID-19 is still going on right now. And I don't know when you're watching this video, but if you are, this video is recorded during COVID-19. And there is no vaccine currently for COVID-19. But there have been articles brought up by some scientists in other places that have said, oh, we found a vaccine, or we've found something that could potentially, help cure COVID, whatever. But none of those things so far has really seemed to be true. It's just that the scientists have done some trials that had some slight successes, but haven't been definitively shown to cure anything. But if you take that paper and you put it out there and go, hey, we found a cure, and people will read it and go, oh, yeah, great, we've found a cure for coronavirus. Woo, we're all good now. When in reality, it's well, okay, we haven't really found a cure. We just did a few trials with this one drug, and it seemed to kind of help some people, but not everybody. But I'm just going to say that it's a cure. right? And now we're putting out false information. So it's really important that we don't do that. Peer review can make sure that that doesn't happen. So that's the main reason. But anyway, that's it for this section of information. Hopefully that helps clear up any confusion on anything. But as always, you can feel free to email me, talk to me in person in class, or reach out. Maybe we can do Google Meet or something, and I can certainly answer any questions that you have. So, all right, guys, that's it for this one. I'm Mr. B. I'll see you in the next one. Bye.